Thank you. Today we'll talk about my current research, which is shadowing in non-uniformly hyperbolic systems. And the first thing I want to do is to define a pseudo-trajectory. If you have a map of a metric space into itself, you call a sequence of points pseudo-trajectory if the distance between the image of previous point and the next point is not greater than d. So basically everything you see in the real world is a pseudo-trajectory. For example, if you are doing like numerical simulations for something, of course your computer makes some mistakes and you get a pseudo-trajectory instead of exact one. Or if you study some physical system, you usually use approximate laws instead of exact. Also, if you consider some measurements which appear like from anywhere, there is a random noise, and you again get a pseudo-trajectory instead of exact one. So a natural question arises, do pseudo-trajectories represent properties of exact trajectories or not? And to answer this question, we will introduce following definition. We will say that a map has shadowing property if for any epsilon greater than 0 there exists d greater than 0 such that any d pseudo-trajectory can be epsilon shadowed by exact trajectory, which means that, well, corresponding points, distance between corresponding points of trajectory and pseudo-trajectory is not greater than epsilon. I will give some examples. The first example of a map that has shadowing property is, well, any contracting map actually has shadowing property. For example, if you take x over 2, it has shadowing property. It's quite obvious. What is a bit more surprising is that if you take expanding map, for example, x to 2x on a real line, it still has shadowing property. Well, this is because usually if you have a good map, then it has shadowing property if and only if its inverse has shadowing property. And since inverse of x to 2x has shadowing property, this one has one as well. Here I want to say that one of the first results about shadowing is that any hyperbolic diffeomorphism has shadowing property. And this is like a classical, well-known result. Now I will give an example of a system that does not have shadowing property. For example, it is a translation on a real line. And, well, it's easy to see that this system does not have shadowing property because, well, your mistake accumulates with each step and expands with the growth of the length of trajectory, and it's a contradiction with shadowing property. Okay, so one of the main things known by now is that shadowing property is kind of almost equivalent to hyperbolicity. And this is kind of a problem because, of course, in real life, you want to study not only hyperbolic systems, but shadowing property holds only for them. So we will have to somehow change the definition, and that's how I do it. I want to study some quantitative relation between different parameters of shadowing: the length of trajectory, the amount of mistake, d, and epsilon, which means how close the exact trajectory goes to the pseudo trajectory. So that's a precise definition. We say that f has a finite Hölder shadowing property if any depth pseudo trajectory of length non greater than d to minus beta has an exact trajectory that shadows it with epsilon equal to d to alpha. Okay, so this is a definition, and there is a conjecture, quite an old one, by Hamel, Grebegy, York, that a typical dissipative map of R2 has a finite Hölder shadowing property with exponents 1/2 and 1/2, which just means that any d pseudo trajectory of length non greater than 1 over square root of d can be square root of d shadowed by exact trajectory.
Sorry, what is a dissipative map?
Dissipative, I won't give precise definitions now, but it's kind of chaotic in this context. Okay, so a theorem proved by Sergei Tikhomirov in 2015 says that if a C2 diffeomorphism has finite Hölder shadowing with exponents alpha greater than 1/2 and alpha plus beta greater than 1, then f is hyperbolic, which means that this conjecture is kind of a best thing we can have, because if we have bigger exponents, then we again get equivalence to hyperbolicity, and well, it's like the same that as the previous definition. Okay, so but the conjecture is still open, and the main goal of my research is somehow to formalize this conjecture and to, well, prove some theorems about it. Okay, now I will define a system which I will deal with. First of all, a Bernoulli shift on the sequences of zeros and ones is just a shift map. There is a natural distance and measure on the space of the sequences. And it is well known that the shift is topologically conjugate to a uniformly hyperbolic system, mainly to Smale horseshoe. Okay, now I will define a linear cocycle. A linear cocycle over T is such a map. In the first coordinate, it's just a shift, and in the second coordinate, it's a linear map, and the coefficient lambda depends on the first coordinate. Okay, we will additionally assume that expectation of logarithm of lambda is non-zero, which in dynamical terms means that well, we don't have a uniformly hyperbolic system, but we have some kind of non-uniformly hyperbolic, and its Lyapunov exponent is not zero due to this condition. Okay, so what we will study? We will study a probability of a random de pseudo trajectory of length n to be epsilon shadowed by an exact trajectory. Okay, so here is a theorem which I managed to prove in this setting. Theorem is following: for arbitrary continuous lambda such that expectation of logarithm of lambda is not zero, probability of that a random trajectory with d equal to epsilon over n to power gamma of length gamma can be epsilon shadowed. This probability goes to 1 as n goes to infinity. Well, you can reformulate it in terms of finite Hölder shadowing, and this means that the system has finite Hölder shadowing with exponents alpha and beta such that, well, gamma is less than 1 minus alpha over beta. A few words about the proof. First of all, we take tilde lambda, which means the same thing as lambda, but it depends only on finite number of coordinates. Then we use Kramer's theorem about large deviations to prove our shadowing result for tilde lambda, and then we choose tilde lambda close to lambda so that our results holds for lambda. Okay, so now I want to explain what does this result have to do with the conjecture. I will introduce another definition. Let's denote by AK a differential of a C2 diffeomorphism in a point f to the k of x. Then we will consider a linear equation, which you can see here, vk plus 1 equals to ak vk plus wk plus 1, where wk plus 1 is a given sequence of vectors, and the modulus of wk plus 1 is non greater than 1. And well, we want to solve this system, find vk, such that modulus of vk grows non faster than polynomial, than some certain polynomial on n. So when we have this definition, I've proved following theorem. If diffeomorphism, C2 diffeomorphism satisfies this property called slow growth property with any exponent gamma, then it has finite Hölder shadowing with with some certain exponents alpha and beta. And now it's clear what the linear cocycle and the result about linear cocycle has to do with the conjecture, because when you consider a diffeomorphism, the slow growth property actually means that there is a shadowing in the linear part of diffeomorphism, which is just a linear cocycle over the diffeomorphism. So if you first prove slow growth property which corresponds to the previous theorem, then you can get finite Hölder shadowing for diffeomorphism itself using this result. So what we hope to do, that to prove that non-uniformly hyperbolic diffeomorphism with for a start one-dimensional central foliation has finite Hölder shadowing. Okay, so to summarize all up, I want to say that the first theorem is about shadowing on a linear cocycle, which is kind of equivalent to slow growth property, and the second theorem is that if you have slow growth property, then you have finite Hölder shadowing. And okay, thank you.
Okay, so my research is about searching for examples of non-uniqueness of solutions in equations or systems of equations of a sort like Navier-Stokes equations. It is well known that it is an open conjecture whether there is a one solution or whether it could be some solutions for it, or maybe the solution that exists only on a finite time or whatever. So our approach is to find some examples of systems where there are two solutions of the equation. And our main scheme of approaching it is of the following way. So suppose you have the equation of a form AU plus the squared term B of UU equals to F, where F is a given function which is in Navier-Stokes a force from some outside, and AU is a linear part. In Navier-Stokes it's U dot minus Laplace of U plus some square function of U, where B of UV is bilinear, so B of UU should be squared. And in Navier-Stokes it is again U times gradient, and all of that applied to U. So of course there should be some it could be harder than that because in Navier-Stokes there is the pressure, and you should make a projection on a non-divergence like a divergence-free functions. But still, for a general idea, our equation should look something like that. So a linear part plus squared part equals to F. And we're going to look for solutions which are expressed as in the form of V plus minus G. So you take V plus minus G subtracted, substitute in the first equation, and you have two equations with plus and with minus. And then the one with plus plus the one with minus gives you only the first equation of the system, and when you subtract it, it gives you the second one. So this way you have two equations on V and G, and you want to solve a system of equations on these things. So our approach is to take some V that the second equation will have a solution, non-trivial solution, because of course G equals to 0 is always a solution to that. So we need to find V such that there is a non-trivial solution to it. Then we have v and g. We substitute it in the first equation and find f. And if this f is good enough, then we have this conditions for which the system has two solutions. So that's a general structure of that we designed to solve problems of that sort. And first, our result was about the dyadic model. So dyadic model of Navier-Stokes equations was introduced a lot time ago, more than 10 years ago, in works of on kinematics of liquids. And it was just said that it is a system that has similar properties, such as turbulence, which is in some way similar to this turbulence in the Navier-Stokes equations. And it is an infinite set of equations, each of them is numbered with n, a natural number. So it is an equation on sequence un, which can vary with time. It is some kind of an analog for if you take for Navier-Stokes equation a basis representation of it, then for basis coefficients, it would be not this exactly, but something on the form of this. Of course, not exactly this, because it would be Navier-Stokes equation, but it is a model of those equations with similar properties. So again, it has the same way as before. First two terms are linear on U, second and third and fourth are quadratic, and in a sense of relation with Navier-Stokes, this system has a parameter beta, which shows you how much the linear part, like multiplication with lambda to the power 2n, corresponds to the quadratic part, which is lambda to the power beta. So the relation between these two parts, if you see how it relates in Navier-Stokes and here, says that B corresponds to the dimensions to the dimension of the space in Navier-Stokes, as B is similar to d plus 2 over 2. So if you look at betas and find some answers, then you hope that it could model Navier-Stokes with similar D. And lambda is just a convergency parameter. It could be any number more than 1. It just gives you the faster convergency over the number. So the question is not whether there is only one solution for this system, because for that setting, it is well known that it's not. There is sometimes more than one. We need the solutions to satisfy the following estimate, like the kinetic energy plus the dynamic viscosity energy is not more than the initial kinetic energy plus the work produced by the force. And the solutions that for which this inequality holds are called Leray-Hope solutions. And for Leray-Hope solutions in Navier-Stokes, we have the similar thing, so it is an analog in this setting. So the question is whether these solutions are unique and whether they exist or not. Before us was known that at least one Leray-Hope solution exists, and that is that could be given by Galerkin's scheme when you take just a finite number and solve it and then go to the limit. It's a well-known result. Then it was known for beta that is not more than 2. The solution is unique, and it corresponds to D not more than 2 in Navier-Stokes. So solved case already for Navier-Stokes equations when you have the dimension only 2. It was proven in 2008 by Cheskidov. And if you take the force equals to 0, then you can show that any solution experiences a blow up as some mathematicians believe this is what should happen in Navier-Stokes. And it was proven that for beta is more than 2, there is only one Liouville solution for a zero force. It was proven in 2014 by my science advisor, Nikolai Filonov. So this is what we started with. You can see that for bigger than 3, for beta bigger than 3, you know that there is some problem with solutions. For beta less than or equal than 2, the solution is unique always. So the question is, what happens in the gap? So what happens between beta 2 and 3? And the theorem that we proved that for beta more than 2, you could find f by that scheme exactly that I described before, for which there are 2 Liouville solutions. We prove it, we take 0 initial values, but it could be modified into any initial values. So it shows that for in this exact setting, for beta bigger than 2, you can find 2 examples. And the idea of an example is the following. So you take the equations and you make u start 1 by 1. So the more the number, so u 100ths starts before u 99ths. And this way you cannot think of it as a limit of a finite system. It is always like energy coming from infinity, because u starts from smaller and smaller moments going to 0. And the scheme is exactly what we had there. You take v, the coefficient, you take it close to a constant function on constant on some parts, and then you take you take one close to it so that the solution still exists. And so we proved that with this scheme showed that there is a solution, 2 solutions for some f. And after that, we decided to try to use this scheme for other systems, and we went to stationary Navier-Stokes, which is Navier-Stokes without changing of velocity. So all the time derivatives should be gone to 0. So we decided to, there are actually 3 examples already of when for the stationary Navier-Stokes there are 2 solutions. And we decided to make one that will be better in some ways, if not the others. So we decided to go to the spherical coordinates and consider a case of axis-symmetrical vector field. So we take v and g as before, as the solution of v plus minus g, and take the radial dependence just 1 over r, so that it would give you the easiest, like all the r's will cancel from, there will be a like power of r will be the same in all the terms, and there is no dependence on phi. So this way you get functions only on phi, and you get a system of 4 equations, because well there is a divergence-free equation and 1 vector equation for u. So for this this w, h, and q, there is a system of 4 equations, and the question is to find some u, some w for which there will be a non-trivial solution for h. After that, you substitute everything and get f. So we tried, you can see that in this system there are sines and cosines. So we tried w in the form of sine or cosine or sine squared, it doesn't actually matter. For all of them, we can solve it. And actually see that there is always a non-trivial solution. So for some non-trivial omega, there is a solution. But for a trivial case, if you take omega equals to 0, not omega, w equal to 0, then you still have, you actually still have a solution. It's an easy one, but it has a problem that our solution doesn't have. So it gives you, when you substitute it back and find f, it gives you a delta function in 0. So it makes it the linear one, where w is 0. It makes it a little bit worse than our result, but actually our one is not that good, so that we would publish it or whatever. It's just a result that shows, well, it's just a result that you could get that delta function out. But still it has some problem in 0. So if you see how it behaves at 0, Laplacian over taken of this thing, or the square of r times its derivative, it would give you 1 over r cubed, which is bad at 0 in 3D. So we believe that there should be some problem in some topological problem, so that you cannot define a solution in the whole area. So our further research will be about finding a topologically like a thing without holes, like omega without holes, for which it would still be a solution. So the further research will be about finding a solution without topological problems. That's all. Thank you for your attention.
Okay, so today I'd like to talk about the research I did in the past few months, and this research concerns self-adjoint extensions of bipartite Hamiltonians. But well, what does this actually mean? As quite often we take motivation from physics. We know that in quantum mechanics the dynamics of a system is governed by Schrödinger's equation, and a solution is then given in this form, and we are interested in this operator H that is a self-adjoint operator. And when dealing with physical problems, we often encounter a problem, namely that from physical intuition we get some formal some formal structure of the operator such that everything works on sufficiently smooth functions. So we think of the Hilbert space as an L2 space, and then we consider subspaces of it of smooth functions. But usually the operators we can then write down won't be self-adjoint but merely symmetric. So we would like to construct extensions of these operators that will be self-adjoint, and the question of how to construct these extensions was completely answered in the first half of the last century by John von Neumann. And he proved that given a closed symmetric operator, the self-adjoint extensions, well, first of all, they exist, self-adjoint extensions, if and only if the dimensions of the so-called deficiency spaces, that is, the kernels of the adjoint minus I and plus I respectively, coincide, and then we can parameterize the self-adjoint extensions by the unitary operators between these two spaces. And well, this shall justify why we are interested in computing deficiency spaces. So well, remember this term, deficiency spaces. And one of the many reasons why self-adjoint operators are particularly nice is that they can be thought of as operators of multiplication. That is, they can be diagonalized in some sense. And yes, now this kind of was the first part of the title about self-adjoint extensions. Now the second part, what is a bipartite system? So again, we take motivation from physics, and we now consider two separate systems and want to know how to describe the composite system when we take these two systems together. And well, physically argued, we can consider the case where basically these systems evolve independently from one another, and then the group of evolution should split in the following sense, that that we just have the tensor product of the first group of evolution and the second group, and it will turn out that if we calculate the generator of this group, it will look exactly like this so-called tensor sum of operators. So this is why we are interested in, well, operators of this form, but now we assume that both HA and HB are self-adjoint, and the question we now want to ask ourselves is what happens if we allow one of these operators not to be self-adjoint anymore. Okay, and this question was dealt with by Ibord, Marmot, and Pérez-Pardo in 2012, and they stated that if we define the operator HIB in terms of this tensor sum, then the deficiency spaces will decompose in the following sense, that we just take the deficiency spaces of this operator that is not self-adjoint and consider the tensor product with the Hilbert space of the second system. However, in their proof, they restricted themselves to the case of the spectrum of HB consisting solely of eigenvalues of simple multiplicity, but this is a severe restriction in the sense that we cannot reduce every self-adjoint operator to this case, so what I and my advisors wanted to do was to generalize this proof to to the case where we don't assume these properties of the spectrum, and well, there are basically three parts that we needed to do in order to prove this. So the deficiency spaces are basically kernels of the adjoint of this operator plus or minus I, so it makes sense to compute how the adjoint of this operator looks like. Then the second point is very technical. We want to construct a family of bases of these kernels of the adjoint of this first operator plus z that depend in a measurable manner upon z. That is every vector of the spaces shall depend measurably on z. Oh, by the way, we are working on separable Hilbert spaces all the time, so we can just consider the usual concept of measurability without having to deal with a more technical apparatus. Okay, and the final part then is to prove, calculate the solutions of these two equations. So we just want to prove how this kernel of the adjoint plus or minus I looks like, and just straightforward calculate these solutions. And for doing this, we note several things that will simplify the proof drastically. The first thing is that, by the spectral theorem, without loss of generality, we may assume that the Hilbert space, the second operator, the self-adjoint operator, is an operator of multiplication. Then the second point that is really useful is that we consider the Hilbert spaces of these two operators, and one of them is an L2 space. Then this will be isomorphic to the so-called Bochner-Lebesgue space of Hilbert space valued functions that are square integrable. and hence we can consider elements of this tensor product as functions and evaluate them pointwise and make calculations as if we were in HA. Okay, so this is kind of the proof. And well, considering the first part, it is quite natural to assume that when we calculate the adjoint of this tensor sum, then we can just take the adjoint inside, and it is given in the following way. So it's the action is quite what you would expect it to be, and the domain is, well, exactly that space where, well, the maximal space where everything there is possible, and the result is still in L2. And it turns out that, well, we in fact have this equality, but well, the proof is rather technical. So the main idea is that we decompose the set omega, or that we consider subsets of omega on which phi is bounded, and hence we know that if you take a bounded operator and, well, some densely defined operator and consider their adjoint, then the result will be just the sum of the adjoints. And we make use of this and of the fact that these sets on which phi is bounded cover omega, and then we get some very technical stuff, but it turns out that, well, yes, the adjoint looks exactly how we wanted it to look like. Okay, so the final part, so this is the third part, because here it only becomes clear why we need the second part. So we deal with this first. So if we consider some element of this kernel of HAB adjoint minus I, so here we are dealing with one deficiency space, the other one where we would replace minus I by plus I is dealt with in exactly the same way. And we know how this adjoint operator operates, and from this we see that pointwise almost everywhere f of omega is contained in this very kernel, but we see that I minus phi of omega is contained in the upper half plane. And so the kernel of this, so the deficiency space will be isomorphic to this kernel. This is just a well-known fact that, well, because this operator is symmetric, the so-called domain of regularity contains the upper half plane and the lower half plane, and the dimension of these spaces will be constant on each connected component of this domain of regularity. So basically what we know from well-known theories that these are isomorphic, and hence we can construct a unitary operator between them. But what we in fact want is a family of unitary operators that is measurable. So we can always construct these V omegas, but it is not at all clear that we can construct them in such a way that this map will turn out to be measurable. But if we have such a family of unitaries, then, well, because they are unitary, we get that, well, this V omega of f will be square integrable, and hence we kind of get a map from omega to the kernel of, well, to the deficiency space of HA, and we also easily see that we can reverse this in the sense that every element of this, well, this L2 space mapping into these this deficiency space admits some representation of this kind. So in the end we have this isomorphism, but we note that this kernel equipped with well, the inner product that is inherited by the well, from the Hilbert space for the system A will again be a Hilbert space, and hence we have this this isomorphism of tensor product with an L2 space and Hilbert space valued L2 functions. But yes, the measurability of this family V omega is not at all clear, but one can prove this by just constructing a basis of these kernels that depend measurably on Z, and this is even more technical. So finally, the core result that I managed to prove together with my advisors Daniel Lenz and Melchior Wirth is that in fact such a family of unitary operators exists, and this then concludes the proof for the general case. This concludes the proof for the theorem that was stated by Ibord, Mamo, and Pérez-Pardo for the general case of HB being a self-adjoint operator. Okay, and the next question that kind of naturally occurs is what happens if we not only let HA be a symmetric operator, but also drop the condition that HB be a self-adjoint operator and also consider it to be merely symmetric. And in 2015, Ibord, Mamo, and Pérez-Pardo conjectured that in this case the deficiency spaces should decompose in the following sense, that we basically take the these tensor products as we considered them in the theorem of this work, where HB was self-adjoint, and then we switch the rows of HA and HB and consider their direct sum. Okay, but unfortunately a proof of this this theorem is still missing, and of course the fundamental part of the proof I presented was that we can diagonalize HB, and this of course doesn't work anymore if we don't know that HB is a self-adjoint. So for this proof one would need to construct a different apparatus, and yes, this is what I am thinking about right now, how to generalize this. And that's it. So maybe thank you for your attention, and do you have any questions?
I don't know much about what you're talking about, but I was reading what you sent us. Can I ask you about it?
Yes.
So you tell that you also have a question which is given to you by your local advisor.
Yes.
And here I read that you have a question, and it has been formulated and proven in a more general setting, and I'm wondering why then you would go to a more restricted if it's already proven?
Well, because this proof is very complicated, and
so you want to simplify it?
Yes.
Okay.
So a main part of this proof that was given there was to approximate elements in some general C-star algebra by elements that have finite spectrum, and of course this question is irrelevant if you consider algebras of matrices that have finite spectrum anyway. So I think this question can be severely simplified. Yes, and this is one thing I'm also trying to do.
So you intend to do this as well?
Yes.
Hello. Today I am very shortly speak about my diploma, because I think many of you heard about it and thought about something completely different, in fact. Okay, let me firstly very shortly introduce my diploma. It was about calculating the type of some Jacobian matrix, some characteristic of Jacobian matrix, for which you can estimate, for example, its eigenvalues and some other. And there was a conjecture about origin type and fragment Lindelöf indicator, but I can't say anything about this fragment Lindelöf indicator. Conjecture about type was proved in different ways, and for me it was calculating. Well, in some work, it was reformulated as calculating of sum like that, calculating this limit. And I succeed to do it, and the research result and short idea to prove is firstly shorten the sum, then consider like exponential ranges with exponent goes to 1. Then there will be a small number of different x's, and then you can use some combinatorial arguments and estimate is quite precise. But I could speak about more, but I already speak about it many times, and it wouldn't be honest, I guess. So let me introduce joint works with Nikita Gaivoy, Alex Davidov, and Sergei Nikolenko. Work is the following. It's not about analysis, but in the end, it will appear a bit. Okay, let us have the following simple model. You have memory, and you have some different type of elements and shared memory. And you receive some elements of some type, but the whole memory have limited size. For example, you have many elements of every kind of memory, and you decide which you will take and which you will discard. And every moment you transmit one element from one queue. And your goal is to transmit as much elements as it's possible. So you decide for which queue you will take element and for which you will discard, and you should take as much as possible. And measure of strategy is competitive ratio. It's a ratio of number of elements our algorithm is taken divided by number of elements the optimal possible is taken in the worst case. Well, it seems like very logical strategy to take as even as possible. So if you receive many elements of each type, it seems to be logical to take from each, let it be B size of memory and M size of queues, it seems to be logical to take this number of elements in each queue. But no one can prove it. Let's call it LQD. It's this open question, what is competitive ratio of LQD? And there were bounds 4 divided by 3 to a best possible online algorithm, because we can't even prove that best possible algorithm with finite memory is LQD. And this bound from LQD, we improved them a bit, and I should say that the upper bound is 2. So LQD is too competitive. Okay, how we achieve it? We consider special type of examples. Let us have an infinite number of queries, and for each query we have segment when someone gives us infinite number of elements to this query, but we don't know when the segment ends. And in every moment, in every second, exactly one segment ends, but we don't know which. But let's consider the simplest case, when in every moment exactly one queue starts and exactly one queue ends. So there are some graphics. First graphics explain how the LQD will work. So it's number of so what does graphics mean? I have some here. LQD take the same number of elements in some queues, and there are queues for which there are no elements now. Sorry, how to say? For which the segment already ends, but there are some remaining elements. And dependence is like that. And dependence from optimal algorithm is like that. This means that we should take only from each segment only in the last moment. And then you can consider another example. Then every moment exactly one packet dies, but they all born in the same moment. And we can't really understand what's going on here, but we make like two types of simulations. First, we maintain a linear time algorithm to calculate competitive price and got some strange constant, like 1, 4, 4, 5, 6, and so. We don't really know what this constant means. It's my question to you. Maybe like nature of this constant isn't like it can be from a different knowledge. But there are quite good online algorithms which have better performance. And empirical is the most possible example, and we don't know why. Also, you can say that LQD in fact converge to this. We can consider different initial states, and LQD will converge to the state very fast, but again, we don't know why. There are graphics of how the LQD looks like in this example. There are like curve of 3 segments. We understand what is the critical point, but we don't understand what is the line between the segment. And again, maybe it's well known to like in some dynamic system or maybe another knowledge. Also, you can like make a reformulation of this problem in the another languages. But first, the formulation is like that. Then we can, another formulation is to like simple compute some maximum of linear function. To maximize some linear functional with some linear inequalities. Well, sounds simple, but we don't know. Okay, thank you for your attention.
Questions? So you still did you read the paper of this guy from the university?
From
Yeah.
This number?
Yes, yes.
Well, I read it, and
Wow.
there are, I think it is correct, but there are much.
I see, I understand you.
So someone else should read it too. It's like, I can guess that upper bound is not 2, but this, but it's in some paper which is quite less known, and maybe it is incorrect, but I don't think so.
Okay, almost all what I'm going to talk about today can be classified as stochastic geometry. So let me first introduce some objects and notions. Let us consider a convex body K in Rn and a random point inside it with uniform distribution. Then we can state the question, how to recover the body from the sample of this random variable of some size n. We will state this question not in all space of all bodies, but in some certain parametric family of bodies. But before, let us see on the another classic object in stochastic geometry is expectation of distance between 2 such independent points. It was shown that in case of ellipsoids, this value, mean distance between two random points, proportional to mean width of the body. So the mean width of the body is the mean projection onto line, and averaging, when I say mean, I mean averaging by Haar measure on the space of lines. The mean width is the one or the first in sequence of natural geometric characteristic of bodies that calls intrinsic volumes. We can define it in several ways. The first is as a coefficient in Steiner formula. So let us see on volume of T neighborhood of some body as a function of T. Steiner showed that this function is polynomial, and we can write a coefficient of this polynomial in the following way. We have some coefficient kappa that just Euclidean ball with some normalization. No, it's just Euclidean ball in corresponding space. And some number vk that does not depend from dimensional. So if we take body k and consider in a higher dimension, then the numbers vk will be the same. So intrinsic volume is just some internal characteristic. And in case nth intrinsic volume, it's just usual volume. And -1 is the square of surface with some n-1 intrinsic volume proportional to square of surface of body. And the first is the mean width. By analogy with the mean distance between 2 points, we can consider a random k-dimensional simplex by sampling k+1 point, independent point. And it's also true that for ellipsoids, not only mean distance, but all mean volume of k-dimensional simplex proportional to corresponding intrinsic volumes. So if we have a sample of points, we can find approximation for mean k-dimensional volume. And then for ellipsoids, we can estimation for its intrinsic volumes. Then naturally arises the question whether an ellipsoid uniquely determined by its intrinsic volumes. Uniquely means in terms of their its semi-axis. So here's a conjecture that was stated by Anna Gusakova and Dmitry Zaporozhets that if you have two ellipsoids in Rn and such that their intrinsic volumes are the same, then they're congruent. And my bachelor thesis was that it's true in dimensional 3. So it can be formulated as if you have two ellipsoids with equal volume, surface square, and the mean width, then they have the same semi-axis. So this theorem shows that conjecture holds for dimensional 3, but in higher dimension it's still open question. I will give you one example that consider another n-parametric family. It's rectangular parallelepipeds. Then in this case, we have a really nice formula for intrinsic volumes. It's just symmetric function. Then by Vieta theorem, we easily obtain the h length from intrinsic volumes. And in this case, and our conjecture is obvious. What's the problem with ellipsoids? That for ellipsoids, there no exists such a nice formula. We have only like that. Let me explain in 2 words. Mth intrinsic volume is the following. You have m copies of Gaussian vectors with 0 mean and covariant matrix diagonal with square of semi-axis on the diagonal. Then the m intrinsic volume is just a mean volume of parallelepiped with h vectors, xi1 and xm. That's explain complexity of ellipsoid case. And in dimension 3, we have a following formulas. So for usual volume, it's easy, just multiplication of semi-axis. For mean width, it's mean length of Gaussian vectors. And from one additional statement follows that second intrinsic volume is it's also mean length of some Gaussian vectors with such covariance matrix. And 2 words about the proof. The main idea was the following. The first, we can prove the local non-degeneracy of this map, which is obtained by computing Jacobian, and it was most complex part because you need to compute Jacobian of matrix, and its entries is integral. Yes. And given that, the proof is completed by the study of topological properties. So we just, in some sense, fixed this we fixed volume and mean width, and we have one curve, and we go along them and investigate this. After I finish this work, I am sometime I'm thinking about higher dimension, but it become really, and it's really fast become more, really complicated, because in computing Jacobian it was really, I really use number 3 in dimension. After that, after some time, I switched to another problem. So again, consider mean distance between 2 points, random points, and denote it by delta 0. And so if we, it's a function with homogeneous of power 1. And if you want to state the equation where it have maximum and minimal, we need to normalize it. And we can do it in several ways. For example, for square root of square and for perimeter of body on the plane as a normalization, it's known answer. So for square root of square, it was known ago, and but for perimeter it was investigated by my science advisor several months ago. So for perimeter answer is known, and the next question is what about diameter? The lower bound is immediately follows from upper bound for perimeter, just because we have some inequality. But the where is the maximum is open question. Current hypothesis that the maximum value achieved in circle, in round, of course. But we can state more stronger hypothesis that not just maximum at round, but we can take Minkowski sum of body k and the Bolarius epsilon. And the function f of epsilon will be increasing function. Of course, from increasing of such function will follow initial, because you can take any body and round in them and obtain that in round maximum. So we can prove that the derivative of f at point 0 is more or equal to 0. Then we obtain the initial hypothesis. And so I, after some work, I show that the initial hypothesis equivalent to such inequality, where delta 1 is the mean distance between points where one from a uniformly distributed inside body and another point uniformly distributed on the border of point. So the first thing that I think that this inequality is very noticeable, because in case of plane you have a constant square divided by perimeter and divided by diameter. I think it's interesting itself. Another important thing that you want to differentiate delta 0 by epsilon. You can write it as integral and split integral into 3 parts, depending on how much points fall inside K. So the first is when both points inside K, the second when one inside and one outside of K but inside the body. And if you look precisely on this integral, you can easily see that it's converged to product of volume, area, and delta 1. And the idea is the term delta 1 naturally arises while you investigating delta 0. So this inequality is still not proven, and in order to investigate, to prove it or construct counterexample, I want to investigate the related inequality. For example, this. It looks like really intuitive. Then if you have 2, 0 inside and 2, 0 and 1 points inside and 1 border, in the second case, the mean distance should be bigger. But it's also not easy, and for example, it is not true point-wise. So you cannot fix one point because you can see this example. So mean distance from this point to the border is half of this interval, but for point inside, more than half. And I also consider this inequality. It looks like more intuitive and should be more obvious. And but for now, I still cannot prove this in for any bodies. Even on the plane, here's some slides about the following. The inequalities that mean distance that we have such inequalities equivalent the following, that you have for any direction you have an equality not for distance between points but distance between projection. And if you prove that for any direction inequality holds, then you prove that for distance it's also true. And it was known before that for distribution inside body, when you project, of course, when you project your measure onto interval, you obtain some probability measure with convex probability density. And it's true that you have this inequality. That the mean distance between projection when density is convex is less or equal to length of interval divided by 3. So my idea was the following. When you have a border and project measure, uniform measure from border, you obtain something like inverse of convex.
So you have 1 more minute.
Yeah.
Most.
Okay, yes. And so I can show the following, that if you have a convex curve and you project onto horizontal line, then you have such an equality. So, and from that follows, then if you have a body with a symmetric x, then for mean distance between projection, inequality holds. And one more what I understand about this problem is that this inequality holds for triangles. And for triangles also we can write some constant between these means. But in general it's not true that you can write constant between those 2 terms. And maybe one more word what I want to talk about myself is a problem that I solve in my work. So consider can you take more? One.
I think we should stop now. Because interesting, yes.
Okay.
That's enough. Are there any questions to the speaker?
Now we So what's the motivation behind your research on this question? Like, why do you consider them? Why are they interesting?
Which one? Not the,
the whole, you know, the whole line of research. Because to me it appears that you know, you didn't talk about two separate questions,
okay,
completely different. No, it's a focus.
What do you mean? So my motivation for myself is interesting.
Sure, yeah.
Yes, but another motivation that this problem is given for me by my science advisor. And so, for example, mean distance between 2 points, as I know, have some application in financial.
Yeah, so
yes.
That was my question.
Ah,
so
yes.
What are the applications?
I don't know. I just know that they exist. I don't know.
Okay.
I just believe in. Yes.
Was all the talk about convex bodies or
Convex. That's all about convex bodies. Because, for example, if you have not convex bodies, you can do like this, and all points from the border, for example, will be here, and the mean distance will be approximate 0. Yes, and about first topic, you should define intrinsic volume as only for convex bodies, because another definition of intrinsic volumes, case intrinsic volumes, it's a mean projection on k-dimensional linear space. So if you take the projection, it's better if you have convex bodies.
I will talk about two things today. So the first is strained planar configurations of necklaces, and the second one is traceable graphs in the plane. So you can see on the slide the formal definition of the configuration spaces of the things we are interested in, but let me explain more casually what's going on. So what is a necklace first? Well, a necklace is a closed string with a number of beads, like number of beads, and some of the beads are fixed. These are the bold points, and some of the beads can move freely. These are the strokes. And so in this case, well, k is the number of fixed beads, and well, what is n is equal to 8. We have 8 beads overall, and it's equal to what? We have three things in the yellow piece. We have 4 things in the blue piece and 1 thing in the red piece. So, and 1 is 3, and 2 is 4, and 3 is 1. Okay, also between the fixed beads you have some lengths. So here say L1 is equal to, I don't know, pi, L2 is equal to 5, and L3 is equal to 1. So this is a necklace. Well, we have three pieces of total length pi, we have 4 pieces of total length 5, and we have 1 piece of total length 1. And now we want to put this necklace on a plane in such a way that the string between every 2 beads is strained, meaning that, well, we have some polygon, like we have this thing, and something like, I don't know, this. Oh, I messed up with colors, sorry. Okay, and then something like this, yeah. Okay, yeah, meaning that, well, the yellow guy is equal to whatever, pi, the sum of the lengths, and so on. Okay, and now we want to consider all such configurations, and, well, we're interested in the geometry of this configuration, so we consider the orbit space under the action of the group of orientation-preserving isometries. Yes, so we have this space, and, well, one can ask, is there always at least one configuration? And the answer is, well, almost. The only obstacle is when our necklace forces us to draw a segment which length is more than half of the total length of the necklace. Okay, so we have this configuration space, and the first question we want to answer is, does the space carry some good structure, say smooth? Well, not exactly. There are several singularities. The first type of singularities appear when two vertices coincide, and the second type of singularities appears when all of your polygon fits into a straight line in such a way that, well, each piece is like the segment of maximal length. Yeah, but it's not that bad, because well, the singularities of the first type are easy to deal with, and the singularities of second type don't appear for generic values of the parameters of the length L. So yeah, and well, actually all the results of my talk today, of the first part, are the generalizations of the results on polygonal linkages. Well, which is in this notation is just when all the bits are fixed. Yeah, they are well studied. Yeah, and for them, well, the first obstacle doesn't appear obviously, and the second do not appear for general L, so they are smooth. Okay, and now we want to study an oriented area. Well, what is an oriented area? You have your origin, you just draw these things and compute all the all the oriented areas of these triangles. You know, yeah, and okay, and we want to think of this function as a Morse function on our manifold. So yeah, and first we describe its critical points. So what is a critical point? Well, first it should be inscribed in a circle, our polygon. Then all the segments of the same color should be of equal length. So let me draw it correctly now. And third, you know, the segments of the same color should go in the same direction. Yeah, but yeah, if we want to think of this oriented area as of a Morse function, then we want some good description of these points, like having n's and l's in hand. We want to enumerate them somehow. We can do this in a very nice way, because it would mean that we know some results around Robin's conjecture, which I think it's well, considered too hard to, you know, there is a polynomial such that if you have a cyclic polygon with these lengths of sides, then its oriented area, and A is oriented area, then this holds. There is such a polynomial. Yeah, and if we have a nice description, then we can like compute this polynomial, but I think it's known only up to n equal to 8. Yeah, but we don't know. But we don't need the description for all n's and l's, because you can like change your parameters smoothly, and your configuration space will also change. And if it doesn't pass to some critical values of parameters, then the homotopic type will remain the same. Okay, so yeah, but now we want to, yeah, as we think of this as a Morse function, we want to compute Morse indices. So, and how to compute them? Let me do it in this example. What is first? Okay, the winding number. We start here, and we go like one time in clockwise order. So winding number is -1. Then what are epsilons? Well, these yellow guys go in clockwise order, so epsilon 1 is -1. The same for the blue ones. And the red one goes in counterclockwise order, so it's 1. Okay, what else should we compute? Okay, this sum? Well, it's actually an oriented perimeter of the polygon that you get when you draw tangent lines. So yeah, and well, it's less than 0 in this case because, well, you have too many sides going in clockwise direction. So finally we get that the Morse index is equal to 1/2. What? Well, we need only on the third guy in the sum is equal to 1, so it's times 2 minus 1 plus 2 minus 1. I guess it should be 1. Yeah, so it means that, well, it's not a point of minimum, but well, almost. Okay, yeah, and now that's what's done for now in this direction. And well, I think I should pass to the next thing because I don't have time. Okay, completely different setting. If you lost me somewhere, you can now join again. So we have a graph. And a realization of a graph is just a drawing of this graph. Vertices are points and edges are segments of non-zero length. So we consider all such realizations modulo affine transformations. And okay, so we have some drawing, say like this, of this graph K4. What is the cell stress? Well, you should think of each edge as of a spring. Yes. So it's either, so you have some forces in the ends of this spring. So you get something like this. Well, the forces on one edge are equal, well, equal by absolute value. Something like this. Well, no, it doesn't work like this. So yeah, and what you want is that nothing moves. Like the sum of the forces at every vertex is equal to 0. And now from these, having a drawing of your graph, you consider all the stresses, and what you care about is actually only the signs of these stresses. So this thing goes out of the edge, so it's plus, it's plus, it's plus, and it's minus, minus, and minus. So you get a collection of pluses and minuses numbered by edges, and you consider all the stresses and get, well, this oriented matroid, but never mind. Yeah, and now we change the, well, now we get from a realization a matroid, and now we fix a graph, fix a matroid, and consider all the realizations that have this matroid as matroid of stress. Oh, thank you. Yeah, in the beginning of this year, my advisor proved the following theorem. Well, there is a formal definition on the slide and the formal statement, but what is actually meant is that, well, these realization spaces can be arbitrarily bad. So it means that if you want to say something about these realization spaces in whole, well, you can't. But still, what happens after such a universal result? Well, the first thing you can think about is, well, these realization spaces for fixed m, for different m's, they stratify all the realization space. So like all the realization space is, well, for oriented matroids. So, and yeah, the first thing you can try to prove is that this stratification can be arbitrarily bad. Not just each strata, but all the stratification. Well, it seems to be unreachable for now, but I don't know. Yeah, but the other direction you can go to is like to find some conditions under which the realization space is actually, well, good. So yeah, and the theorem we managed to prove with my advisor is the following. Okay, so you have a graph which is free connected and planar, which means that it's a graph of some polytope. So it has faces, and you also say that it should have a triangular face. So, and now we consider something like this. Okay. Yes, and you ask what? Well, if the graph is free valent, then it's kind of obvious that there is no more than, if you fix some s here, then there is no more stress with this fixed s on this edge. And yeah, now you consider all the realizations that with only these two stresses, and well, like with one-dimensional space of stresses, and you get that it's actually a ball. Yeah, that's what we managed to prove. And yes,
1 minute at most.
I think I can finish. Okay, that's all. Thank you.
Thank you. Are there any questions?
Yes.
So what are your future plans? You proved the theorem. It's interesting.
Yeah, it's about the first one or the second one?
Second or the first.
Okay, the plans here. Yeah, I said about this thing, and also, well, this theorem doesn't seem to be very like general condition. So probably there are also, well, other conditions under which the realization space looks nice. Yeah, and this is something we can do. And for the where to move from here, yeah, so we have almost a Morse function. We know it's Morse indices, and well, what we can do is to compute homology of these spaces using Morse complexes. Yes, but for this, as I already said, you need some description of all the critical points for fixed n's and s. You cannot get this probably, but yeah, well, you can get this in some case. Like in my thesis, in my bachelor thesis, the description was obtained in the case like M and L 1L, meaning that, well, you have like this thing and something like this. Yeah, it turns out that these the critical points correspond to the solutions of some polynomial equations. Like you take the Chebyshev polynomial of second kind and say that it should equal to something. And yeah. And of course, in the general case, you also can say that, well, these are the solutions of some polynomials. But these polynomials are not anymore Chebyshev polynomials of second kind, and you don't know much about roots of some random polynomials. Okay? Yes?
Would you please show the last slide? What are ABC? I don't understand.
A, B, and C are two vertices. Three vertices, yeah. And you have a face, a triangular face. Yeah, like this one.